we're going to talk about calculus, and hugely important part of mathematics, hugely helpful in so many areas of business, finance, engineering, science, etc. When we did the functions and graphs earlier, we used calculus for a few things, mainly to find the maximum and the minimum point. Now think about that. Think about how often people are interested in the max or the min, the best, the fastest, the quickest, the least cost, the most beneficial, the highest whatever return. All of those things are done by calculus. So without calculus, we wouldn't know when a curve is turning. Are we at the maximum point or the minimum point? Things like even, virus and vaccinations and COVID and all those things. When can you see the thing turning? When can you use your calculus? So behind all of that, there's a lot of calculus. So what I'm going to do now is I'm going to go through the topics in calculus. Again, we're going to take these on a topic by topic basis. We're going to start with calculus and some of the differential rules. And in calculus, what we do as well is, in this topic and in others, I develop a set of, we have a set of tools that we use. I didn't develop them, but they're there for you, and we're saying, what tools do I use when I'm going in to solve a calculus question? And luckily, we're allowed to bring in the tables. The tables are hugely beneficial. Make them your best friend. Look at the tables and say, get used to having those with you for all the questions between now and the Leaving Cert. What do I look up? What do I transcribe? How do I use it, etc. You don't have to learn any of them by heart. And you get marks for identifying which one you want to use in a question. And you get marks for transcribing it incorrectly, and then marks for plugging in the numbers into it. So really what a lot of the questions on your course are about are, what are they looking for here? What tool do I use? What numbers do I plug in? And then you go about it. So that's what we're going to do. So we're going to start with differential rules. So we're idling. This is the first set of tools. I'm looking at the tables that I have, the log tables that I can bring in, and I can say, when I'm differentiating, dir here, k dir here, first differential, to first derivative, if the term is fx is x to the n, then f dash x is n times x to the n minus 1. So f of x is x to the n, or y is equal to, remember that we only have two variables, y and x, vertical and horizontal. So if y is equal to x to the n, dy dx, or f dash x, you take down the n and you reduce it by 1. And that's it. So if y is equal to x to the 3, dy dx is given by this formula as 3x squared. And that's what we learn. There are others then for when we've got something more complicated, when we have something multiplied by another, something divided by another, or if we want to simplify something on its own and do it that way. I won't explain these yet, but I'll use them when we need them. So I'm going to keep this as a really valuable page. I'd suggest that in your log tables you get used to highlighting this section, saying that's a page that I really get used to. And I'm going to keep that as an important toolbox when I go in to solve a problem. It's like an electrician coming into a house to fix something. He or she will have a whole set of tools. They'll have phase testers, and they'll have screwdrivers, and they'll have cables and all that stuff. Or a plumber coming in with spanners and wrenches and all that stuff. So that's your toolbox, and you're saying, that's all they give me, that's what's in the tables, that's what I'm going to use. It's got to be one of these. So I'm going to keep those for later. Now, just so we see these, sometimes they'll write a question as y is equal to f of x, and sometimes they'll say y equals, say, x squared minus 2x minus 8, or sometimes they'll say f of x is. And the derivative, or the differential, or the dir here, or whatever you call it, can either be written as dy dx or f dash x. It's the same thing. So, what have you got to be able to do? Differentiate 3x cubed minus 7x squared minus 4x, plus 4x. So y is equal to 3x cubed minus 7x squared plus 4x plus 7. So you might just write down the answer for that. So give that a go. Okay, so the rule says, well, this is what it says. If it's x to the power of n, it must be this. So if that's x to the power of n, I'm going to take down the 3 and call it 3x squared. And because there's 3 of them, I'll multiply by 3. For the x squared, I'm going to call that 2x, but I'm going to multiply by minus 7. For x to the power of 1, well, 1 times 1 minus, that's 1 minus 1, that's x to the power of 0, and that makes it a 1. So therefore, I get, that just becomes a 4. And if I differentiate a constant, it goes away. So I get 9x squared minus 14x plus 4. 9x squared minus 14x plus 4. Now I can go through it in step by step. I take down the 3 and I get 3 to the minus 1. I take down the 2, I get 2 to the minus 1. That would be 4x to the 1. 1 minus 1, and the 0 would be 0, and they'd cancel. But that's how you differentiate. So that's the first one. That's a nice question, and there could be questions as straightforward as that. Now let's differentiate this one. Slightly more complicated. And we say x cubed plus 2x squared plus 3x to the minus 2. So you might give that a try. Well, again, we say, well, can we use one of these tools? Yes, we can. It's the x to the power of n. They're all x to the power of something. So x cubed, we take down the 3 and we get 3x squared. The x squared, we say, we take down the 2, that becomes 2x, multiplied by 2. X to the minus 2, well, no reason why we can't use the minus 2. So it becomes minus 2x to the minus 3. But there's 3 of them. So we get 3x squared plus 4x minus 6x to the minus 3. And that's how that works. So again, we just take down the number. So really, we have to have very, well, great confidence, I suppose. X is equal to, let me just take this one here. This says y is equal to x to the n. dy dx is n to the x n minus 1. So what would happen if it was y is equal to x to the 17.6? We'd be unlikely to be asked it, but we could say dy dx is equal to 17.6 x to the 16.6. Or if y is equal to x to the half, dy dx is, well, it's just a number. Half times x to the half minus 1. Or a half times x to the minus a half. Or if somebody said dy dx, y is equal to x to the pi, dy dx is pi times x to the pi minus 1. Or if it was x to the elephant, it would be elephant times x to the elephant minus 1. So it's just a formula. You say, this is what it says I should use. This is what I'm going to use. Here's my toolbox. That's what I'm asking. And that's it. So we can see how that works in the following questions. Differentiate 4x to the half plus 2x to the 3 over 2 with respect to x. So how do we do that? 4x to the half, 2x to the 3 over 2. We say, this is differentiation. What does the logbook say? Oh, differentiation says if it's this, I use that. Okay? So, if y is equal to, well then dy dx The 4 stays down. The half comes down and it becomes x to the half minus 1. And the 2 stays down and it becomes 3 over 2 times 3 over 2 minus 1. Half minus 1 is minus a half, and 3 over 2 is minus 1 is a half. And that's how you write it. And that's the answer. Just plug in the same. There's nothing new going on. They're just applying it to different questions. That's all. Now, we now look at the next question. We find this in the exam. We say differentiate 1 plus 3x by 4 minus x squared with respect to x. And we look at the tables and we say this doesn't work. This looks like something, a y or an f of x equal to two things, something multiplied by something else. So if it is, I say dy dx is the first one times dv dx and the second one times du dx. Okay, I'm going to use this tool. I haven't used it for a while. Okay, we're going to do it, and we're going to say that's the product rule. Differentiate 1 plus 3x 4 minus x squared. So I don't like it, but I'm going to call that u and call that v. So I'm going to say, I'm imagining that that's the same as u and v. So I'm going to say u is equal to 1 plus 3x, v is equal to 4 minus x squared. Now remember that what's happening here is that we're saying I want dy dx of this. The examiner doesn't know about u and v, didn't ask about u and v, so if you're going to use u and v, you better use them and then get rid of them at the end, almost like a catalyst that comes in, does its job and then leaves. So I'm making u equal to 1 plus 3x and v equal to 4 minus x squared. So I'm going to write these down here in this zone that I'll have to come back to. So u is equal to 1 plus 3x and v is equal to 4 minus x squared. Now if I'm going to use this formula, I'm going to have to get dv dx and du dx. So if u is equal to 1 plus 3x, what's du dx? Well, if y was equal to 1 plus 3x, dy dx would be, well, that would disappear, it's a constant, and that would be just 3. But that's just a variable on the left-hand side and a variable on the right-hand side. There's no reason it has to be y. So if u was 1 plus 3x, du dx would be 3. So du dx is, I write down as 3. Now, in this case, I've got v equals 4 minus x squared. Well, if y was equal to 4 minus x squared, dy dx, the constant will be nothing, and the x squared will be minus 2x. Well, it'd be 2x and there'd be a minus there in front of it. So there's no reason why that couldn't be v is equal to and dv dx. So dv dx is minus 2x. So I've written those four numbers safely, put them away, because I'm going to need those again on the next page. And here they are on the next page. But I was asked for dy dx, and dy dx from the tables is this. So I say, I'm now going to transcribe that. I'm just going to copy it, letter for letter, into here. And I'm going to get marks for that. The examiner is going to say, identify the right one, transcribed it properly, yes, marks. Now dy dx is going to be u dv dx plus v du dx. But here I've got this code. So I'm going to be very careful. I'm going to go into the zone and say, okay, dy dx is u. U is 1 plus 3x, that's that. Times dv dx is minus 2x, that's that. Plus v is 4 minus x squared, that's fine, and du dx is 3. So I've now copied that out, and the examiner said transcribed it properly, fine. And even if you make a mistake, he or she will follow you the rest of the way, and you won't use any more marks. So that's fine. Now it's a question coming up for air and saying, how do I multiply these things out? Well, I'm just going to expand it. 1 by minus 2x is minus 2x. 3x by minus 2 is minus 6x squared. 4 by 3 is 12, and minus x squared by 3 is minus 3x squared. So now look at this, and I can say, well, I've got a 3x squared and a 6x squared. They're both minus, so that's minus 9x squared. I've got a minus 2x and a 12. So dy dx And note what I've done here. dy dx is equal to this. There is no mention of u or v in the answer. So it's a complete answer. The u and the v have gone. The magic is, it's been used, come in, went disappeared, and that's my answer. So I've got that right. Now, just for this particular question, the original question I think was y is equal to 1 plus 3x by 4 minus x squared. You didn't have to necessarily use the product rule. You could have said, I'm going to multiply those things out. You could have said, I'm going to use the FOIL method. So 1 by 4 I think is 4. 1 by minus x squared is minus x squared. 3x by that might be 12x. And 3x by minus x squared would be minus 3x cubed. So if y was equal to minus 3x cubed minus x squared plus 12x plus 4, and you were asked to find the differential of that, derivative of that, you could have said they're all of the type of the x to the power of n stuff. So I would have said dy dx is equal to, well, 3x squared by 3 be minus 9x squared. The 2 would come down as 2x with the minus, and the 12x would be 12. Minus 9x squared minus 2x plus 12, it's the same thing. Now, they might have asked you to do it with the product rule, but just to prove that it does work and everything is fine there, that's another way of doing that particular question. Okay, so you're in the exam and it says differentiate this. 3x over 2x plus 3 with respect to x. So find dy dx of that. And you say, you look at the tables again, you say, well, it's not an x to the power of n on its own because it's something over something else. It's not a product here, but it looks like this is something over something else. So that looks good. I'm going to use that one. That seems to work. So I've got a u and a v, and dy dx will work out. Okay. So y is equal to this. So I'm going to make the top bit u and the bottom bit v. So using exactly the same approach, I say I've made u equal to 3x. So I better write that down here because I just made this up. The examiner doesn't know about u and doesn't really want u in the answer. V on the bottom is 2x plus 3. Now, I look at the formula that I'm going to need, and the formula says I'll need a du dx and a dv dx. So I better calculate these here. So u is equal to 3x, what's du dx? Well, I don't know. But if that was y, if y was 3x, dy dx would be 3. So that's just a variable on the left-hand side and a variable on the right. It doesn't have to be y. It could be u. So then du dx would be 3. And similarly, if v is equal to 2x plus 3, if y was 2x plus 3, dy dx would be 2. So if v was equal to this, dv dx would be 2. So I've written down what my codes are for my use of u and v. And I'm going to bring those to the next page. So here they are again, and I'll need them. But I want to get dy dx. And I go to the log tables and I say dy dx is this. That's the one I'm going to use. So I identify that and I copy it in, transcribe it in here exactly. And I get marks for that, just as it is. So I'm going to get marks for that. And now I have to say, okay, now I'll plug in the answers. So I go into the concentration zone and I say, okay, v is 2x plus 3. Du dx is 3 minus u is 3x, dv dx is 2, over v squared is this squared. And now I just do the multiplication. 3 into 2x is 6x, 3 into 3 is 9, minus 2 by 3x is 6x. And in this particular case, the 6x and the minus 6x cancel. So I end up with dy dx is 9 over 2x plus 3 squared. And that's important. Okay, what have I got? I've got dy dx only in terms of x's. There's no u's, there's no v's there. It's sorted. I'm done. Now, here's another example of differentiation, and we're talking about differentiate y is equal to 5 minus x squared cubed. And you say, don't know if I like that one. And you start looking up the tables and you say, it's not there, and it's not there, and it's not there. And really, this is a way you can do is, if you see something in calculus that you don't like a 5 minus x squared or something like that, very often you can say, let u be equal to 5 minus x squared. And it just simplifies it. Now again, you're making it up, but du dx here would be, well, if that was y and that was x squared, be minus 2x. And we just write that down. But also, y used to be equal to 5 minus x squared here, cubed. If I say u is equal to 5 minus x squared, y is equal to u cubed. So that seems like an easier question. If that was x cubed, it would be easier. And similarly, if u is equal to that. So what have I done? All I've done is I've said let u equals this. So that's my trick. U is equal to 5 minus x squared. If u is equal to this, then I must get du dx of it. So that gives me minus 2x. But I've also decided I don't like doing this one on its own. I'm going to say y is equal to u cubed. Well, if y is equal to u cubed, dy du is 3u squared, because if it was y is equal to x cubed, it would be 3x squared. And again, I use that as my trick. Now, what I'm trying to do here is I'm calculating dy dx. But all I have is dy du and du dx. And if you look at the two of those and you say that's dy du, that's du dx, if I multiplied those by each other, the bits on the bottom would cross, on the top, the du and the u would cross out. So I'd be left with dy dx. So effectively all I need to do is multiply dy du by du dx. And I'm going to do that. Dy du, I'm told, is 3u squared. And du dx is minus 2x. So that's my answer. But there's a small problem with this answer in that the u is there. And I can't have u there because I made that up. But u is equal to 5 minus x squared. So if I put that back in, and everywhere there was a u, I put in 5 minus x squared, I'd get 3 times 5 minus x squared by minus 2x. And now I've got dy dx, just in terms of x's on the right-hand side. And now I've solved it. So again, sometimes you can do this. Sometimes you see a trick for doing this. Sometimes it's helpful. You don't always have to do it. There are other ways of doing it. For example, in this question here, you could have said y is equal to 5 minus x squared cubed, which is 5 minus x squared by 5 minus x squared by 5 minus x squared. And you could have multiplied them all out and then got the dy dx in the normal way. But I'm just saying that at any time in calculus, if you find something tricky, just make it equal to u. And then, write your notes down here and then make sure you get rid of the u at the end of the day. So let's look at something here. Differentiate y plus the square root of 1 plus x with respect to x. Now, because it's differentiation and there's a plus there, you can see this as one part of the question and this is the other part. So the y equal to x is easy. dy dx is 1, so the first part is going to be a 1. But now let's look at the other part. Y is equal to square root of 1 plus x. Well, the square root of 1 plus x by the square root of 1 plus x must be 1 plus x. So therefore, this must be 1 plus x to the half by 1 plus x to the half is 1 plus x to the 1. So another way of writing the square root is 1 plus x to the half. Now it's still messy, but imagine if we decided that u was equal to 1 plus x. Then we just have y is equal to u to the half, and that might be an easier thing to do. So what I'm going to do is I'm going to let u be 1 plus x. U is 1 plus x, du dx is 1, because that was y is equal to 1 plus x, dy dx would be just the 1. Y is equal to u to the half, because I've made it just this bit here. So dy du is a half u to the minus a half. So that's my sort of my zone that I'll come back to again. So here I have it on the next page. I have these zone, and I say, now I want dy dx. How do I get dy dx? I have a dy du, and I have a du dx. And luckily, one of the du's is on the top, and one is on the bottom. So I can get dy dx by just multiplying. So dy dx is a half u times minus a half by the 1. The 1 was actually the, well, we have it here. dy du, I come down here, is a half u to the minus a half. Du dx is 1. But I have to finish it because I can't leave u there. So u is 1 plus x. So dy dx is a half 1 plus x to the minus a half. And then that's that question. Now I think the full question, I think, had a 1 in there as well. So the overall result was y is equal to that plus that. I'm adding back the first answer plus the second one. Or if I wanted the minus a half, I could have written it as 1 over the square root as well. Because x to the minus a half is 1 over x to the half, which is 1 over root x. Just a different way of writing it. That's all. Now, here's another example of differentiation. And here they say, they give you a function where they say y is equal to 3t cubed and x is equal to 4t squared. Find dy dx. And you start looking here and you're saying, this is really not any of these that I have here. How do I solve that? Well, it's giving me y in terms of t, and it's giving me x in terms of t. So I could probably get dy dt all right, and I could probably get dx dt. So let's see how that works. Well, dy dt would be, I'd take down the 3, be 3 squared by 3, or 9t squared. For the x part, if that was y is equal to 4x squared, it would be, I take down the 2, but dx dt is equal to 2t by 4 be 8t. But I'm looking for dy dx. So I've got dy dt, I've got dx dt. And really what I'd like is I'd like the dx on the bottom. So imagine if I knew that, well, dx dt is 8t. If I put this over it, I'd be bringing the dt up on top. So I'd get dt dx is equal to 1 over 8t. I just flip it. Like if I've got something like a quarter, and I divide 1 by a quarter, I end up with 4 over 1. I just flip it. Okay, so if I flip that, I get dx dt. Okay, now I've got dy dt and dt dx. If I was to multiply that by dt dx, I'd have a dt on the bottom and a dt on the top, and I'd end up with dy dx. So that's what's going on here. I've got y is equal to 3t cubed and x is equal to this. dy dx is dy dt by dt dx, or dy dt over dx dt. So effectively what I can get here, I can say that so let's take the first one. Y is equal to 3t cubed. If y is equal to 3x cubed, it would dy dx would be 9x squared. So I write that down as my code. X is equal to 4t squared. Dx dt, if that was y and 4x squared, it would be 8x. Dx dt is 8t. So I've got all my code here. But dy dx is dy dt by dt dx, or dy dt divided by dx dt. So they'd cancel. So dy dx is 9t squared over 8t, which is 1.125t. Now, when you're looking at your notes, I've realized that I've left out the following slide, so just bear with me on this. I'll show them to you now where it's done, but you might want to add these into your notes. So you might want to take these down while you're working through it. But this is the right answer. dy dx is right, but you see the way I still have t there? So I really can't have t there. I need to get that back into x's. So I'll have to make that into x's in some way. So I have an equation that says x is equal to 4t squared. And what I'm going to do is I've got to make t into x's. So this is what I do. X is equal to 4t squared. What is t? Well, I don't like t, so x is equal to 4t squared. 4t squared is equal to x, but I just want t. So to get rid of the 4, I could divide by 4 to get t squared. And to get rid of the square, I just take the square root. So t is equal to the square root of x over 4. So I go back to my answer here, 1.125. I should change that by 1.125 times square root of x over 4. So now I've got dy dx fully on the right hand side without any mention of the thing I used in the middle, the t. And that's the parametric function example. Okay? So how do we do derivatives and derivations of questions? What we're doing is we're saying we are given a whole load of formulae in the tables. Use the ones in the tables. Okay, not these. You'll have them, get familiar with them. So if it's x to the n, it's n times x minus n. If it's log, it's 1 over x. It's e to the x, it's this. If it's any one of these, you just look at these derivatives. And equally, when you come to trigonometric functions, if you differentiate them, you'll see that the differential of tan x is x squared x, etc. And all of these are given. So what's happening is they're asking you to say, can I differentiate something? You don't have to learn these off by heart. You just have to know that there's a grid that you can use for these questions. So let's see how we use those skills. Here we've got a differential question. And we say differentiate y is equal to sine 3x plus log x. Y is equal to sine 3x plus natural log of x. How do you do that? Well, what you say is there's nothing that I haven't done. Maybe I haven't done this particular question, but it's not new to the syllabus and I have the skills for it. So y is equal to something in x. It's not one of the standards x squared. It's not a product. It's not a quotient rule, but it's trigonometric. So the first thing you say is let's start looking up the tables. Let's see if I can tidy these up. And bear with me a second while I get them again. Just tidy them away there too quickly. These are your tools. This is your toolbox. These are the pages that you highlight in the log tables that you're going to be using. And you're saying, okay, they've asked me a question. So the approach to the calculus questions is this in the tables? And you look up and you say, let's look for sine 3x. And you say, oh, I see a sine here, that's good. But it's not 3x, it's just x. Okay, so that's not great. So instead of 3x, I'm going to say y is equal to sine u. I'm going to say u is equal to 3x. I've got rid of something that I don't want. I've called it 3 is u. So u is 3x, du dx is 3 in my tables. Y is sine u. If y is sine u, what's the derivative? Cos u. Well, sine x and cos x, sine u must be. So dy dx must be cos u. So this is what I write down. Now I'm still using u here, but that's okay. Now dy dx is going to be dy du by du dx, just as we did with the chain rule earlier. We're just going to swap it to get rid of it. So dy dx is cos u dy du, we look up here, because sine and cos, they were from the tables. We just copied those down. So cos u times 3, or 3 cos u, but remember that we don't want u in the answer. So u is 3x, so 3 cos 3x. So it's more the approach that I'm interested here. What is it? Can I look it up in the tables? Now that was only the first part. That was only the sine 3x part. What about the log x part? So now we say let y equal to log x. How do I find the answer for that? Again, we say, where did I put the tables? I think I put them here somewhere. So you say y is equal to log x, the derivative. And you say, oh, it's here, great. It's natural log, yes, natural log, it's great, it's here. So if y is equal to, remember that y is fx, this is dy dx. So if y is equal to log x, dy dx is 1 over x. So dy dx here is 1 over x. So the original answer was 3 cos 3x plus 1 over x. That's it. And that's how you do the differential questions. And we'll use exactly the same approach when it comes to integration. We'll say, I know some of them, I don't know the rest, I'm going to look them up in the tables, use the one that I've chosen, etc. So I might just take a breather for a minute, and we'll start then with distance, speed, and acceleration. Great. I think you can hear me now. I just had my mic switched off there for a moment. So I'm going to take a breather now for a minute, and I'm going to talk about the syllabus and about the practical questions that come up on the course in mathematics. And these are very similar from one year to the next. When they decide to change the syllabus of the mathematics course way back in 2015, and it hasn't changed substantially since, they decided to make the questions more practical in calculus. And one that made a lot of sense was talking about speed and acceleration, and how things like that about problems of getting somewhere to a certain place as quickly as possible. And that's how they did the questions. So I'm going to show you an example now, and I'm going to ask you a few questions, but there's nothing particularly difficult about this topic at all. And I'm going to just ask you to bear with me while I just change the screen and you can see me without the background. And I'm just going to get a prop as well. I'm going to get a little ball that I can throw up in the air. So bear with me a second. So, hello, you're most welcome. I'm here against a plain background and I have a ball with me. And I just wanted to show you a few things about some of the questions that they can talk about. Most of you may not be doing physics, or some of you might be. You may well be doing physics as well. But if you're not, there are terms that we use in the maths question that we talked about speed and we talk about velocity as well, speed or velocity, and we talk about acceleration. So what they typically ask is they ask about, say, a ball being thrown up in the air. So they throw a ball up in the air and it goes to a certain height and then it falls down. And they're interested in three different functions. One is the height of the ball. Height of the ball is measured in meters, like distance. And the speed of the ball is how fast the ball goes up at a certain time. And acceleration is this gravity pulling it down. How quickly does it change its speed? So if we think about speed and acceleration just for a moment, imagine that you live in Limerick and you're 200 kilometres from Dublin and you're driving to Dublin. You would say, how far is Dublin from Limerick? You'd say 200 kilometres. That's just distance. That's kilometres measured in like meters, it's distance. If you drove to Dublin in 2 hours, you'd be driving at 100 kilometres per hour. So that's distance per time. D distance, D time, dx or dy dx. That's the derivative. That's the first order derivative, the first differential in k d here. So that's dy dx, and that's called speed. And if you're doing, say, 60 kilometers an hour on a certain road, and you then slipped into the motorway, and a few seconds later, 6 seconds later, you were doing 120 kilometers an hour, you'd be changing your speed from 60 to 120, 60, 70, 80, 90, 100, etc., up to 120. Your speed would be changing per second. So if your speed was changing, then the second derivative, d speed dt, or d2x dt squared, would be changing. Okay, so that's how you get it. So in these questions, they talk about speed, acceleration, speed and acceleration and distance. Now, back to the ball for the moment. They often have a camogie player, or they have somebody, a missile going up into the air or something like that, and then it falls down, or train braking hard on brakes and something like that. But typically what happens is when they watch the ball going in the air, there is something magic about the top of that flight. So for example, when I throw the ball in the air, it goes up and it goes up a certain height and then it falls. And you're asked to find out what happens at the top when it falls down. Well, it runs out of something. Well, the height, how do you find the height? Well, the height of the ball at the very top is when the speed is 0. The speed that used to be here, fast, 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 and then it stops, and then it runs out, and then it falls. So the first derivative of the distance, it's no longer going up, it's coming down. That gives us, so when the speed is 0, we can find out, in other words, the turning point, we can find the highest point. What happens when the ball hits the ground? Well, it's still under acceleration, and it still can be quite fast. So the speed, we don't know what it is. But we do know that the height above the ground is 0. So when we find the height above the ground equals 0 on the height function, then we can find out what time that's at. So we can find out if a camogie player hits the ball in the sky or something like that and then it falls. If we know when it hits the ground again, and we know the curve, the function, then we can find out what time that was at. So that's really all that's going on. The questions are fairly similar from year on year, but it's knowing those various concepts of speed and distance and time and velocity. It's really quite useful. So I'm going to start the question. I'm going to change the screen again, coming back into the notes. Is that okay? So I'm going to turn to sharing my screen. And just bear with me a sec. I'll stop the share for a moment. I'll just change my own screen as well. I'll just go back into, and I'll just take, I'll just imagine that I'm coming from Griffith College, Cork. Okay, though I am at the moment based in Dublin. In fact, a lot of our classes this year, when I say that, have been delivered around the country because virtually everybody was at home. So most of the courses were delivered from either Dublin, Cork or Limerick, you know, to the country as a whole. So I'll just turn now to share my screen, and I think hopefully you can see this and you can see my hand again, and we're back. Okay, so thanks very much for that time. Now let's go with calculus, distance, speed and acceleration. So here's an exam standard question where distance is measured by s, often used in physics, and t is represented by t in time. Find the velocity. You'll find that the velocity is given by ds dt. And acceleration is the change in speed, so it's the second derivative of the distance. An observation from physics: if you throw something up in the air, the highest point it reaches is the point when its speed is zero. So when ds dt, when it's no longer changing its distance from the ground, when the distance dt or ds dt is zero, then it's at the maximum. So we start now by saying a missile is fired up in the air. The height h meters of the missile above the firing position is given by this equation here. You are asked in the exam question to say, find the speed of the missile after 10 seconds, the acceleration of the missile, and 1 second before reaching its greatest possible height, the missile strikes a target. Find the height of the target. So, we're given a formula for h is height in terms of t. Find the speed, the acceleration, and what happens before it hits the max height. So we start by doing the main work on this. H is equal to t into 200 minus 5t. Now you could imagine that this was a y equals uv equation, but I think it's easier to multiply in. So I'm just going to say h is equal to 200t minus 5t squared. So this is our equation. And a useful thing to do at this stage is to call that my height equation, or the function. You might call it the function, or you might nearly call it y in your own mind. The next thing you're interested in is find the speed. Well, to get the speed, it's the change, it's kilometers per hour. So you want this per dt. So let's get dh dt. dh dt of 200t is 200. And t squared would be 2t. By 5 would be 10. By minus would be minus 10. And that's called speed. And that'd be dy dx. Really is what you're thinking about. Or f dash x, whatever you want. And that would be fx. And the second one then would be d2h dt squared. This is acceleration. If you differentiate a constant, it goes away. Differentiate 10x would be 10, minus 10 would be minus 10, and obviously it's dt, so it's just minus 10. And this is acceleration. So what you've done is you've really solved an awful lot of this question by just writing the three equations out on a page like that. Now I'm going to put those aside because we're going to now start doing the exam question. Find the speed of the missile after 10 seconds. I have to find speed. So we go through the notes and we say, okay, the speed is given by the rate of change of distance. H was 200 minus 5t squared. V, or velocity or speed, was dh dt. Differentiate 200t, we get 200, 5t squared minus 10t. However, the question said, find the speed of the missile after 10 seconds. Not the speed of the missile, but the speed of the missile when t is 10. So now you've got to go back here and say, really what they were looking for here is not this. That's the speed of the missile. But when t is equal to 10. So when t is equal to 10, we put the t equal to 10 into this. So now we go back and we say, okay, when t is equal to 10, it's 200 minus 10t. T is 10, so it's 200 minus 10 times 10, 200 minus 100 meters per second. And that's the first part of that exam question. The second one then is find the acceleration of the missile. The acceleration of the missile, we did it by differentiating it again. So we do that. So we differentiate by saying, well, the differentiation is, that's the speed. And sorry, the acceleration, sorry, I have it here, apologies. there's the actual equation for speed. I differentiate the 200, it goes the minus 10t, I get minus 10. That's meters per second squared because it's acceleration. Okay, and what was the question? Find the acceleration. It didn't say find the acceleration at a certain time. I don't have to plug in t. Well, there's no t there anyway, so that's fine. The next question is, 1 second before reaching its greatest possible height, the missile strikes the target. Find the height of the target. Well, its greatest possible height, where does that happen? Going back to the ball, when did the ball just stop going up? When the speed was 0. So to find the greatest possible height, I've got to go to the speed equation, which is this. And I want the speed equation to be equal to 0. So that's the equation for speed. When is the speed equal 0? When the thing has run out of energy and it starts to fall down. So 200 minus 10t is 0. 200 equals 10t. T is equal to 20. Because 10t is 200. Don't like the 10, divide by 10, etc. 20 seconds. So 20 seconds is the max this would last without falling down. But I think the question said 1 minute or 1 second before its max height or something like that. What was the question? It said 1 second before reaching its greatest possible height, the missile strikes the target. Well, if its greatest possible height is 20, after 20 seconds, 1 second before must be 19. So really what's going on here is find the height of it after 19 seconds. And again, it's important to go back to your notes here. You said t is equal to 19, but which formula do I use? Do I use acceleration, speed, or height? And it says find the height. That was the question. So in all of these, you start looking and say 1 second before, find the height. Height, I need the height formula. Find the height at a certain time. So you say this is my height formula, 200t minus 5t squared. I want it when t is equal to 19, so I just plug 19 into that. So that's how it works. So there's my formula for height. I want to plug in the number 19 for the t, and I find 1995 is the height. So that's how they work. And the exam questions are very similar to that, whether it's a camogie player or a rocket going up in the air or whatever. Okay, now back to calculus and integration. We're going to use very much the same approach as we did on differentiation. We're going to lean on the exam tables. The general rule for integration is that if you integrate x to the n, you go up a number and divide. So if you integrate x cubed, you go up 1 and divide by 4. Whereas before, you would have come down and multiplied. So for example, if you had y is equal to x to the 4 over 4, dy dx, you'd say, take down the 4, and you'd get 4x cubed. If it was divided by 4, you just end up with the x cubed. So that's how you do it. Now, the other thing you have to add in is a constant, because the integral here is x to the 4 over 4 plus a constant, plus 2, 3, 4, 5, 6, because regardless of what that number would be, if you were to differentiate it, the constant would disappear. So every single form of this plus any constant after it would give you the same integral there. So that's why we say if we don't know the limits, we put in a plus c. If you do know the limits between a and b, what you do is you get x to the n plus 1 over n plus 1, and you start by putting in the values of the top limit, and then you plug in the values of the bottom limit, and you take the bottom from the top. So it looks very long there, but we'll do it, and it's sort of easier when you do it with actual examples. But that's the full formal way of writing it. So the integral of f of x, and that works for an awful lot of equations. So we're back to like we were with differentiation. We say integrate this. So you might want to give that a go for a minute. Just integrate that for a second. So we say, what do we do? Well, the only formula we know is this one. So if that's what the formula says, or this is what the formula says, well, we do it. So it doesn't look like there are any limits, so it's not integrating. So we're just saying the rule of integration here, we're saying there's no limits, so we can plug in the plus c. So what happens to x squared? Well, the x squared will become x cubed over 3. 5 of x is really x to the 1, so that will become x squared over 2, and there'd be 5 of them. And the 4, you just put an x in beside it. So we get x cubed over 3, the minus would stay the minus 5, x squared over 2, the 4x plus a constant. And that's the general formula. And again, it wouldn't matter if it was x to the 17, we'd say x to the 18 over 18 plus c. Now here's an integration within limits. Here we say integrate x squared minus 5x plus 4 with respect to x between these limits of 4 and 6. So here's a nice graph. And we say, okay, x squared would become x cubed over 3. The 5x would become 5x squared over 2. And the 4 would become 4x. And now we've got the limits of 4 and 6. We actually write them like this with square brackets, like absolute value brackets around them, 4 and 6. So we're going to start by putting in the 6's on the top, everywhere there's an x, so that x cubed becomes 6 cubed over 3, 6 squared over 2, and 4 times 6. And now we do the same, plugging in the values of 4. This is just arithmetic, really. And we do all the sums in between, like 6 cubed is 216 over 3, which is 72 or whatever. That's just a calculator. So let's assume that we're doing that okay, and we end up with 8.666 infinity on that. So that's our answer. So if we were to draw a picture of it, that's actually the graph of x squared minus 5x plus 4. That's the nice shape of the quadratic. If we draw the integral of it, it's the area between 4 and 6. And we can see here that this area here, the value at 6, if we were to plug it in here, if f is equal to 6, we could find that value, 36 minus 30 plus whatever that would be, plus 4, so that would be 10, 610. And when x is equal to 4, I think we get 4 squared minus 20 plus 4, which I think is 0. And that's the shaded area here. Now, it's not quite as big as a triangle. If it was a triangular piece, I'd say it's 2 squares by 10 up. So half the base by the perpendicular height would be 1 by 10, which would be 10. It's not as big as 10 because you can see there's a bit missing there because it's a curve. So 8.66 looks right. So that's the integration with limits, and that's really useful thing about integration. Integration allows us to find out the area under a surface. Hugely valuable. So integration within limits, here we go. We say integrate also x squared minus 5x plus 4 between 1 and 4. Exactly the same calculations, x cubed, etc. We're just using the numbers 1 and 4 now. And we plug in the numbers, and we get minus 4.5. Which seems strange, but it's minus an area. But if we look at the graph, we can see that what's happening there is that the area is seen as below the line. So areas underneath are seen as negative. So it's minus 4.5 is what we got. But it's just showing a sign. But it's actually a physical area of 4.5. So, and then just to compare this with the trapezoidal method, this is a formula, again, you can see the tables are given to you. So if you were to do this with the trapezoidal method, I've chosen the values of f of 1, f of 2, f of 3, and f of 4. and they gave me those points here. If you were to work out the area using a trapezoid, you can see there the shape of either triangles or rectangles. What is the area in the red? It's not going to be as big as the full area in the curve. And the formula in your tables for the trapezoid is, you say, again, what you say here, there's a formula for this. I can look it up. I just need to know how to use it. So the formula is given as h over 2 y1 plus 2 times all of this plus y2. And what that means here is that the gap between them is h, a step of 1 all the time. So in this case, h is 1. So the area is 1 over 2. You start with the first value for the y, which is 0. Then it comes down to here, here, and then up. So it looks like we've got a y0, y1, y2, and y3. We only have 3 in total, or 4 in total. So you put them all in. The last one is 0. The first one is 0. 0 and 0. And the bottom two, I think, were at -2. So that's where they were. And we get an area there of -4. And we can see that the area of 4 there is slightly different to the area of, I think we got 4.5 when we did it with integration. We got 4.5. So the curve was a little bit more than the trapezoid. And that makes sense because it covers all those little white bits there are included in the curve, but not in the trapezoid. Okay, so how do we do integrals of functions? Very much the same way as differential. In that what we have is we've got a whole series of formulae pages that we can look at in the tables. So it's a different set. Make sure you're looking up the right one. Make sure you're looking at this is the fx and this is the integral. So these are the integrations. Okay, similar and not differall. So, and again, we've got a whole load of these for various cos's and sines and all that. Okay, and you go to the table so you make sure that you get them right rather than these notes. And again, trigonometric functions here as well. So you see a whole load of them here. And other fancier ones as well. So you just have to see if you can spot one in it. So let's do some calculus integration. Now, these pages I'm going to keep. I'm going to keep highlighted because I'll be referring to these as I do the questions, and I'll be saying, is this in the log tables? Okay? Or something like it. So, integrate fx is sine 3x dx. Integrate fx, and the integral of that. So, integral of sine 3x dx. And you say, well, should I know this? No. Is this in the log tables? I don't know. So you say, let's go looking. And on this page, you say, oh, the integral of sine is there. Oh, that's great, but it's sine x. It's not sine 3x. But I prefer it with sine x, so I'm going to say, let u be 3x. And if that's the case, then I've got the integral of sine u. Now I have to be careful. I've got to figure out what dx is. So I go down to my tables here again and say u is 3x. That's my cheat or my catalyst or my link. So u is 3x. If u is 3x, du dx will be 3. Or dx is du over 3. Well, how do I get that? du dx is 3. du is 3 dx. Dx is du over 3. So in this case, I said, I don't like the dx on the bottom. I'm going to multiply it up on both sides. I don't like the 3 on the top. I'm going to divide. So what I've done there is I've found out one in terms of the other. So if I'm going to integrate something, I can't have x's and u's in it at the same time. So if I change one of them into a u, I better change the other one into u's as well, because all I have in the tables are things for really the integral of sine x dx, not du. So I've got to make this into something neater. So I'm going to integrate that. So sine 3x dx becomes sine u for the 3x, but the dx becomes du over 3. And 3 is just a number. It's like it's a third, so it doesn't matter whether it's on one side or the other. I can take it out. So it's a third. Sine u du. Sine u du is nice in that I think, yes, I have one of those. I can integrate that. And that's telling me that if I integrate it, it's minus cos. So that'll be minus cos, and a third of it is a third, plus the c for the constant. Now again, I'm not finished, because I'm leaving my answer. I've got to check, am I leaving anything in here that I shouldn't? I'm leaving the u in here. Yeah, but the u is 3x. So I now substitute back, and I have it. So that's the approach. That's the approach that I use. And let's see if I can continue that approach in other things as well. The questions look more complicated, but the approach is just a matter of, I suppose, reassurance and confidence in yourself that says, look, this is all they can ask. They can put something up. There's got to be a link in the tables. I'm going to go to the tables and see where it is and then use it. Integrate from 0 to pi. So in this case, I've got limits. Sine squared theta d theta. Well, I'm not going to find theta, but I might find x. And it's saying find sine squared. So I go looking and I say, I don't see it there. I don't see it there. Oh, great. I see it here. I see it as sine squared. That's good. So I found the integral of that, and it's this. Okay, it's messy, but it's there. Okay. So I'm just going to copy that. So what happens now is I say integrate this. So the integral of sine squared theta d theta is this. All I've done is I've copied perfectly. Instead of where x was, I'm putting in theta and 2 theta, but I transcribed it. And it's between the values of 0 and pi. So I now have everywhere, I have to do this twice now. I have to do it for the values when theta is pi and when the values of theta is 0. So the first one is pi over 2, because that's theta over 2, minus half. Sine 2 theta would be sine 2 pi. Here I've got 0, and here I've got sine 0. So I can work that out. That 0 is going to disappear. Pi over 2 is okay. And sine 2 pi, I think sine, I'd have to check that out, but I think sine of 0 is 0 and sine of 2 pi is 0. So I end up with pi over 2. And there's a graph of it. Just happen to draw the graph of y is equal to sine squared x. And you can see where's the integral of it or whatever, between 0 and 2 pi or something like that. Oh, sorry, I was integrating between 0 and pi, just between here and here. And how much did I get? And I can work out what that is. Now, the next page is a bit of some tricks, and they give you some of these as well in the tables. And you can see, are any of these tricks being used? So if you see any of these. So again, if somebody says integrate, let's take the first one. If somebody says integrate 1 over x squared plus 9 between 1 and 3 dx. You'd look up this and you'd say, can't see it. Oh, but there's one of these, x squared plus a squared. Well, if a squared was 9, a would be 3. Therefore, I can look up the example of that and integrate it, because x squared plus a squared in the tables, they've told me is this. So if a was 3 in this case, I'd say 1 over 3 inverse tan x over 3. And then within the two limits and put them in and whatever. Now they're longer, but they're just trying to put you off. Similarly, if somebody says it's 1 over 16x squared plus 9, that looks like a square of something, like 4x by 4x. 4x by 4x plus a squared. I could make that, I could say u is equal to 4x, and then I'd get u squared plus a squared, and then I solve it that way. If it's this one here, a bit trickier, and again you might look at these notes and say, how do I spot it? But 1 over x squared minus 6x plus 10, it's a bit tricky, very tricky, but again it's a trick that they've used, so you might just familiarize yourself with it. That's nearly a square. It's x squared minus 6x plus 9 is a perfect square, and then 1 is another square on top of it. So that's x minus 3 squared plus 1. And again, another trick, and 25 minus x squared is a squared minus x squared. So they're just trying to hide them, but have a look at those. What you do here is I suggest that you've done a lot of integration. You're looking at exam questions, you're coming up with them, and you go through some past papers and you say, I can't do that one. You go to the exam state commission papers, you go to the solutions on them, and you say, that's the trick, that's the substitution. And say, all right, okay, I must keep my eye open for one of those. That's it. But it's the same technique. And here's the last one that I'll do before we do an exam question or two. Integrate from 0 to 3 of the square root of 9 minus x squared. And what they do here is, this is the last one here. And what they do for this trick is they say 9 minus x squared is the same one here as 25 minus x squared. It's 3 squared minus x squared or something like that. And they say you've got to change the a value for just 5, and you've got to change the x for a sine theta, and so it's tricky. So what they do here is integral of this. If it's one of these, it's a trick. You've got to say which one is it, and you said, okay, well, I think the a squared is the 9, and the x has to be changed. So you're told that from this trick here, and these are the full set of them, there's no more. Basically you say, okay, I should change the x into a times sine of theta. So I'm going to change the x, in this case I'm going to change the x to a, which is 3, times sine of theta. So x is 3 times sine theta, x over 3 is sine theta. Now, x over 3 is sine theta. Theta is inverse sine x over 3. You know how to get rid of a sine, you just do inverse sine on both sides. When x is 0, we'll find out what that value is, and when x is 3. So really what we've done is, in this question, we have changed it from 0 to 3. We've said, instead of 9 minus x squared, we have 9 minus 9 squared theta, because x was 3 sine theta. So we get 9 minus 9 sine squared theta, square root it. And then dx, how do we get dx? Well, we have to figure that one out as well. Thought I had it there as well. But x is equal to, x is equal to, x is equal to 3 sine theta. What's dx d theta? Well, it's going to be 3 times something. We look at sine, and I think the derivative of sine was cos theta. So dx would be 3 times cos theta d theta. So this dx becomes, so that's what happens there. Dx is, because we would have done that in differential. So now we put them all in, we get, it's all of this times 3 cos theta d theta. But we've got to change the limits. When x was 0, theta was 0. We're plugging in the values now. And when x is 3, theta is inverse sine 3 over 3. What's inverse sine 3 over 3? Pi over 2. So inverse sine of 1, how do you get the theta? Inverse sine theta is inverse sine. When you put 1 over 1 in your calculator, get the actual number. You might find it's 90 if you have it 90 if you have it in degrees, or you might say it's pi over 2. So 0 to pi over 2. So now the integral comes from 0 to pi over 2, all of this. Now 1 minus sine squared theta. You might remember that cos squared plus sine squared theta is 1. So 1 minus sine squared theta, if we took that over, will be cos squared theta. And the square root of cos squared theta will be cos theta. And the square root of 9 would be 3. So 3 times cos by 3 times cos is all of this, 9 cos squared theta. 9 goes on the outside, cos squared theta. How do you find the integral of cos squared theta? Don't know. You look up the tables again. You look up the tables and you say, oh, it's there, it's given. So you can write it down, and then you plug in the values of 0 and pi over 2. And there's your answer. And there's the graph of it. There's the graph of y equals the square root of 9 minus x squared, and there's the area. Now, that was lengthy, but think about what was happening again, and you'll need to do some practice on these. But what we're saying is that you get an integral, and you say, can I look up the tables? Can I make a substitution? And then at each step, you then say, plug in the values. And that's how the integration questions are done. So with a few minutes to go to one, let's just see if we can do some exam questions. And remember that all the exam questions are on the state exams with the solutions. And indeed, the challenges that people had along the way and where all the marks were. So we start with find the integral of 4x cubed minus 6x plus 10 dx. There's no limits, so you're going to have a plus c and you just plug them in. X cubed is x4 over 4 times 4. 6x is 6x squared over 2 plus 10x plus c. And there's nice marks for that. Part of the graph of, this is 2019, part of the graph of a cubic function is shown below. The graph cuts the x-axis at 3 points, A, B, and C. Given that f dash x is 6x squared minus 54x plus 109, show that f of x is equal to this. Well, if that's f dash, how do you get f? You integrate. So we're going to integrate that for a moment. And how would you do that? You change the x squared to x cubed, divided by 3 and multiply by 6. The 54x will be x squared over 2, so that'll be probably minus 27x squared. The 109 would be x. But you've got to prove that it's equal to minus, there's a minus 126 there, that the plus c bit is equal to that. But you know that the point 2, 0 is on the curve. So if the point 2, 0 is on the curve, then you know that f of 2 is equal to 0. So when you put in f of 2 here for x, you'll get it equal to 0. And then you can find out what this magic number is there. That's how you could, at the moment you might have said that was plus c. But 2 times 2 cubed minus 27 times 2 squared plus 109 times 2 would be equal to something. Plus c would be 0. You'd be able to find out what the c was. Having done that, find the coordinates of b and c. You now know what you're asked to find the coordinates of b and c. Well, you might know what one of the roots is. X equals 2 is a factor, or sorry, a root. X minus 2 is a factor. X minus 2 is a factor, so therefore you divide x minus 2 into the x cubed thing, and you find a term in x squared, a quadratic, that you solve to find the other 2 points. Okay. Let's just briefly do this, and it'll be a minute or two after one, and then we'll stop. The number of bacteria in the early stages of a growing colony can be approximated by n is equal to this. N is equal to 450 e to the whatever. Find the number of bacteria in the colony after 4.5 hours. When t is equal to 4.5, plug it into the equation. So 450 e to the 0.65 times 4.5, calculator, that's the first part. Find the time in hours that it takes the colony to grow to 790. 790 is what you want to be equal to something. 450 times e to the 0.065 times t. How do you solve them? Well, I'm interested in t, so how do I find that t? Well, I don't like it up there, so the first thing I'm going to do is get rid of the 790, I suppose. I'm going to divide it by 450. So e to the 0.065 t is equal to 790 over 450. I really don't like e there. How do I get rid of e? I take the log of it and the log of it. This gives me 0.065 t equals log of this. I don't like the 0.065. I'm going to divide on both sides. That's a number, that's a number. Log you hit on your calculator, divide by a number, you find what t is. Using the function this, find the average number of bacteria in the colony during the period from 3 to 7, 3 to 10. If I want to find out the average of a graph, I really have to sort of integrate between, say, let's say this is on my XY graph. Bear with me a second. Break in a sec. Let's say the graph is something like this, and I want to find the difference between 3 and 12 or something, this area here. I'll really have to integrate. So what this question is really saying is integrate this equation. So integrate 450 e to the 0.065 t. And I say, how do I integrate? I look up the tables, and the integral of e is e and all that. If I'm using not just x, but this, I'll have to change it maybe with u or something. Maybe u is equal to 0.065 t. So it's e to the u, and I have to work that out. But again, between the two limits, between 3 and 12. So I integrate that, and then I divide by the distance between 3. Well, I can do it between 3 and 12 when I've solved my integrals. That's how I do it. Find the rate at which it is changing when t is 12. What does it mean when the rate is changing of a function? It's saying find dy dx. So if nt is equal to 450 e to the 0.065, find, if that's f really, or y, find dy dx. So now we're saying find the derivative. Again, you say 450 is fine. What's e to the x? Well, I don't know what e to the that would be, but I can look up e to the x. I look up the differential tables, and I say, oh, it's just e to the x again. If it's e to the u, I'll have to change for the numbers, and that's it. After k hours, the rate of increase is greater than 90. When is k greater than 90? So you'll have found an equation for n of t, and you'll say, whatever it is, that's the general equation. And you'll say, when is that greater than 90? And then you solve. The number of bacteria in the early stages of a different colony is given by this. Different equation, same question, different one, just different values. Where do they cross? So in one question, you've got a graph like this. And another question, you might have a graph like this. And where do the two cross? Well, you can say it's going to be e to the whatever 0.065, so many of these equals so many of these, e to the 0.17. How would you do that? You would just say, let's say somebody says 17 times e to the 2 is equal to 15.6 times e to the 1, or e to 1.7 or something like that, plus whatever. Well, let's say just like that. How would you do it? Well, you might decide to put all the e's on the other side here. If you divide this by e squared, you could divide this by e squared. Divide this by e squared, you get 15.6 times e to the 1.7 minus 2, or e to the minus 0.3. And then you're left with just that bit and numbers, and you should be able to take the log of it and solve it. So sorry about that being a very quick whistle-stop tour, but basically all the questions and all the answers are there. Hopefully what we did today in calculus brought some of it back, and encourage you to realize that really differential is, what do I differentiate? Do I know it already? No. Look it up at the tables, copy it across, make a substitution, and go with that. And the same for integration. Just more formulae, spot the one you want to use it, get marks for taking it down, and best of luck with that. So good hour you live and enjoy your lunch. And we'll see you back here at 2. Slán go fóill.